I'm a senior scientist at PROS, and I'm happy to share with you my research at PROS of dynamic pricing with hybrid linear contextual bandit model. And this is a collaborated work with my colleagues, Ravi and Justin. So what is dynamic pricing? Right? Actually, dynamic pricing is everywhere around us, right? From booking an air ticket to booking a hotel or rent a car, right? So you notice the price changes from time to time, right? Also, when we shop online, like on Walmart or Amazon, on any e-commerce business, the price vary also, right? And also for the ride-sharing business, right, there's some surge price charges, right? So actually, in fact, many industries have dynamically varying their prices to drive additional revenue growth. Then the question becomes, how can we do dynamic pricing, right? So one way to do it is through a willingness to pay estimation. So you can see here there are, for example, 4 segments of population, with each population have very different distribution of willingness to pay, right? And then from this distribution, we are able to estimate the curve of purchase probability for each segment. Right? Basically, you get the cumulative function, you revert it, and then you get your purchase probability. So this purchase probability basically means when we set a price, we know that what's the probability or the likelihood that the customers in that segment is going to accept that price. Well, in the static pricing setting, well, you just set one price over there, and hopefully it's optimal. Right? And yeah, there are also lots of optimization on top of that to come out with the optimal price, hopefully that fit all segments. And you know that it's not true, well, or maybe it's not properly set for the green segment. Right? It's obviously low for the green segment. Well, in the dynamic pricing case, we will set a flexible prices for different segments. So segment here will also serve as the context for pricing. So that's the information that we find will be relevant to find the optimal price, a different optimal price for different segments. So this is one way to do dynamic pricing. Well, in reality, there are lots of challenges to go with this approach. Right? So the first is, there's no historical variation of prices, right? For many businesses, if they want to adopt dynamic pricing, but they haven't done this in the past, right? So historically, the prices show little or no variation at all, right? So you maybe just observe some noise around 1 dot over here. So it's impossible to accurately estimate the purchase probability. And also, as I have shown earlier, right, different segments will have different curves. Right? So we need some model that can utilize this contextual information to derive these different prices for different segments. So to solve these challenges, we need exploration. We need smart exploration of prices. And this exploration has to be contextual. Right? So what we need is a model that can do contextual exploration. So we have tried a contextual multi-arm bandit model. Right? So I will go through this model with you. For example, if we have a base fare to begin with, like $20, right? And there are some contexts that will be relevant we consider for the pricing. And then each arm basically is the price option, right? So the first arm is a 10% discount, second arm is 5% discount, and fourth arm is like 5% increase, right? And every time when we pull an arm, we will observe a reward. So the reward here, you can think of it as a revenue, right? So the revenue when you put out this price. And then this blue dot here is kind of like the mean of all the experiments you have done in the past, right? So you can estimate a mean of your experiments of pulling that arm. And then from here, because it has to be contextual, right? So we basically learn assume a linear model, right? So the linear model will map from the context to the reward, right? So you will also notice this over here. Because we want exploration, right? We don't want, well, in the beginning, the price just gets stuck and maybe some bad choices, right? We need some type of exploration. So where is the exploration from, right? So the exploration is from the uncertainty estimation. So over here, you can see this upper kind of like the upper confidence bound that can be derived from the covariance matrix of the linear model, right? So on top of that, we will append this upper confidence bound. And then the next time to decide which arm to play, right? So we will pull the arm with the highest upper bound. So it's basically a very optimistic choice, right? So we basically choose the arm with the highest possible reward we are going to get. And when we play this arm, and then we will observe a reward, and then we are going to update this model, right? So the expected reward will change, the position will change, and also the uncertainty, possibly the uncertainty around this arm will shrink. Right? So that's the idea of the contextual multi-arm bandits. We also find that, because this is a kind of like a independent model, right? Because each arm is independent, but for pricing, the prices needs to be, there's lots of correlations among prices. We want to capture that as well, right? So we need some hybrid model to capture the correlations among the prices. And that's why we propose to use a hybrid linear UCB model. And then you can see here, there's a global term of context of Z. So this is some global feature set. And beta is the global parameter to be learned across all the arms. And the X are the price-independent features. And theta will be learned just separately within each arm. And you can see here the Z. So what's Z, right? So Z are all these price-related features, right? The P and P squared. So we introduce a quadratic term to hopefully capture the first increasing and then decreasing trends as we increase price. Right. So this is our model. And then the next question is how we are going to update, or how are we going to find to solve this problem, right? To learn these betas and zetas. Well, it's going to be an online update process. Say there's going to be a t times iterations of updating the model, right? And every iteration, we are going to first observe a context, right? So the Z, the price-related features, and X are the price-independent features. And then we initialize the model first in the beginning, just with identity matrix or zero matrix. And then later on, just based on this observation, we are going to play an arm, right? So which arm to play? Well, based on this, right? So we need to calculate what's the upper confidence bound for each arm under this setting, right? So you can see here, so this is basically that hybrid model, right? So you expected a reward of playing that arm, and this is kind of like the standard deviation, right? That we want to estimate the uncertainty around the reward. Right? And putting it together is our upper bound. And we are going to choose the price, the arm, that gives us the highest upper confidence bound. When we choose this arm, we are going to observe a reward, right? So we say, OK, put out this price, right? And then the customer will say, OK, it's too high, I will reject it, or I will accept it, right? And then we will observe a revenue flow, right? So it will be a real valued payoff, right? So this is a revenue feedback. And then once we observe this payoff, we are going to update all these A and B's in order to derive the zetas and betas for the next round, right? So you can see, so all these models parameters are going to be updated according to this context and the reward observed, along with the arm, which arm has been played. Right? So this is an iterative process. Well, in the beginning, we observe the context. We basically gives our optimistic choice, right, based on current model settings. And then after we observe a reward of revenue, we are going to update our models. So you can see this is an iterative process, right? You need some interaction of the system. So in order to validate this, we basically first simulate the data, right? So in the simulation, we need to know what's the true willingness to pay in the data. Right? So this use case is, I think, also is very closely related to us. Right? Whenever you book an air ticket, right, you may also notice there's some additional options for you to purchase baggage or seat selection or Wi-Fi. Right? So these are called airline ancillaries. Right? So we basically simulate for that case. So in the beginning, we first simulate the traveler and trip profiles. For example, whether this flight is short or long distance, and you book it 3 days before departure, and the flight is going to leave on a Thursday, and it's not a continental flight. And then based on that, we will sample a lot of these kind of the profiles or context for pricing. And then based on these features, we are going to calculate the willingness to pay mean from that. So this is basically a preference-based, because we also train the preference model to predict whether this traveler will like that itinerary or not. Right? So that model is going to give you some preference score from 0 to 1. And then the willingness to pay is based on, OK, if the traveler likes that a lot, and then it will have a high willingness to pay, or it will have a relatively lower willingness to pay. Right? And then based on this mean, we are going to sample the willingness to pay from the models. So once we got this simulated data, we apply our algorithm and to see how much additional revenue we are going to get by adopting the dynamic pricing. So this is our results, right? So we set a base price of 40, and we explore 8 pricing options, and we train the models in a batch of 500. You can see here, so this is the base price, base fare, and we actually compare all the algorithms based on the relative regret. So the relative regret basically means like how far the accumulated revenue is off from the optimal you can get. Right? So that's why the optimal, because we know the true underlying willingness to pay, the optimal regret will be always 0. There's no regret. Right? You can see the base fare regret is like 15%, and then the global optimal. So I basically like kind of try all the options and to see which one setting gives you the highest revenue. Right? So here it turns out the $34 gives you the highest revenue. So it's still 9% off, because it doesn't consider the contextual information. Right? Once we adopt our linear UCB models, so here is our hybrid model. So as you can see, it's still like there's a 3 additional % improvement over the static optimal model. Okay, so here's the conclusion of this talk. So we basically propose the contextual multi-arm bandits with hybrid linear UCB. And this is specifically designed for the scenarios when there's no price variation, and is able to kick off the price exploration efficiently and converge to different optimal price for different segments. And the future work is to develop nonlinear contextual bandits. Right? So this is a linear assumption. And next, we are going to develop, for example, the logistic bandits for this type of problem. And currently, we are also actively developing this into a product, and it's going to put it in deployment for an airline we serve. And that's it. Thank you.
Yeah.
I'm wondering what's a possible
So you see the first slide, right? So actually, lots of industries are adopting dynamic pricing for as long as you do any, for example, online e-commerce selling, right? So you want to vary your price, right, according to all the feature or contextual information for your products. Right? So as long as you want to sell anything, this is a good fit for that. Yeah.
Wait.
So another application, I work in electricity and electricity pricing. So I guess one of the questions that I have is I feel like a lot of the applications of this don't have like a dynamic fixed cost. Is that something that you've looked into? Because the fixed costs for like electricity are based on some other industry. So is that something that you're going to be looking at with like a nonlinear system, or?
Yeah, so you mean like how to incorporate cost in the?
Yeah.
Yeah, so I mean, if you just think of this model, right? So here, the rewards we directly, put out with revenue, right? So if there's a cost here, you can change the objective of the Bandit model to say like the profits or some margins, right? So you want to, you can, yeah, so one advantage of using the Bandit model is also you can design what objective you want to optimize and choose that as your reward.